Welcome to this December session of the Python and Research Tutorials. My name is Jamaica Marshall, and I'm very pleased to serve as the Python and Research Programs Manager. Now, these tutorials have been going on for quite a while, and we have some experts who've been with us in the past to lead these notebooks, and we have a new expert joining us, and I will let them introduce themselves very shortly. First, I would just like to say, if you have not downloaded and installed Anaconda, please don't try to do it during the tutorials. I suggest that you just wait until after we finish today's session and then go back and download things so that you can pay attention during the active parts of the session and can ask questions as we proceed. And I see someone else has just joined us. So let me do my introduction again really quickly. Again, welcome. My name is Jamaica Marshall, and I'm the Python and Research Programs Manager. Thank you all for joining this December session. All right, we are going to go ahead and jump right into introductions to our mentors. We'll be doing 3 notebooks today. And let's start with Lordrick, who will be one of the 2 co-leads for Notebook 1. Lordrick, please give us a quick intro.
Oh, thank you, Jamaica. Good morning, everyone, and good afternoon if you're further away towards the west. My name is Lodrick. I'm a PhD student at UC Santa Cruz, and I work on fast radio bursts, which are the coolest astronomical phenomena, but in my biased opinion. But yeah, thank you, and I'm happy to be working with all of you today.
Wonderful, Lordrick. Thank you so much. And fast radio bursts are pretty awesome. But our next 2 mentors may have something different to say about what they think is most awesome. I'd like to welcome our newest Python and research mentor, Boji Dara. Boji Dara, please introduce yourself.
Hello, yes, so I'm Boji Daran, or Boji for short. I very recently graduated my master's in astrophysics in the same program as Geronimo, actually. That's how I ended up here. And my work is focused on, broadly speaking, galaxy evolution, more specifically speaking, ACD fitting of very distant galaxies at high redshifts, which are much cooler than bursts, in my opinion, but okay. We can have a little rivalry.
All right now, thank you. See, there we go, right there. Wonderful, wonderful. And our last but not least, leading Notebook 3 is uh one of our past experts who's joined us for every single tutorial that I've led over the past 2 years, and that is Geronimo Calderon. Welcome, Geronimo.
Hello, hi everyone. Yes, I am Jeronimo. I am originally from Colombia, but I did my master's in astrophysics between the University of Rome, the University of Nice, in France, and then I stayed here in France for my PhD, which I just started. I have been doing my PhD for the last 2 months, and there is a long way ahead, but already enjoying a bunch. And I actually don't have a prefer the astronomical phenomenon because I work mostly in developing astronomical instruments. So I work with astronomical instrumentation. So I'm more on the engineering side where we provide the instruments for guys like Boji or Lordrick to observe their targets. So yeah, very excited to be here once more. And yeah, thank you so much, Jamika, for hosting this.
Absolutely. Thank you so much. All right. And so these are your Python and research mentors for session 1. Let me go ahead and let me check and make sure I see we have other people who've joined us. Thank you and welcome. All right. Let's go ahead into Notebook 1. Notebook 1 is going to be led by Lordrick, and we do have a co-mentor who's going to lead that session. The second section, I don't see them at the moment. So let's just start with Lordrick going through tuples. Whenever you're ready, Lordrick, thank you so much.
Thank you, Jamaica. I just want to ask you a quick question. How many minutes exactly do I have? I want to set a timer.
I have this going until 10:15. 10:15 Pacific. So about 45 minutes for you, 45 minutes for Paradito for the second part of Notebook One.
Okay, so 45 minutes it is. So 1 second.
Absolutely.
Okay, let's get started. So, as mentioned before, my name is Lordrick Ahinga. I'm a third year PhD student. I have been working with Python going on 10 years, and I learned Python in not in a class, but in a workshop much.
Uh-oh.
Oh, I thought it was just me. Okay.
No, it's not. I thought it was just me also. Lordrick, we've lost you there.
Time where I'm sort of not in the notebooks yet. I would like everybody to open their Jupyter Notebooks. That is if you have installed all Anaconda and all the other required software plus the PyaR notebooks. If you have not yet successfully installed it, once again, don't worry. There will be mentors to help you with that. I was thinking about it in breaks, but probably after the session would be the best time. And so while I'm doing this, while I'm sort of yapping around for the moment, you can try and open the Jupyter notebooks. All right, so these are my Python essentials. Like I said, I am kind of semi self-taught because I had the one workshop, so I was kind of taught, but I kind of picked up a lot of things along the way. These are the three things you need to learn if you want to use Python for science. You want to learn the data structures, that's the lists, the arrays, the tuples. We're gonna see a lot of those today. The dictionaries and all these things. Once you know these few things, you have the very basic, but this is a very good start. After you know that, you want to learn conditional statements and loops. Conditional statements are essentially telling the computer, do this when this is happening, or do that when this happens. And then we also like computers because they can do things over and over and over again without getting tired. You want to do sometimes in science, you want to do something a billion times. You want to do something a million times. It would be very hard to do it by hand or using a calculator. Computers are really good at that, and so you want to learn loops. Once you have Python data structures and loops, you then want to to broaden that, you need to learn functions. And functions are basically just when you want the computer to remember what you're telling it to do. And then you'll have libraries, which are basically functions that people have made for specific purposes. They've spent a lot of time making these codes. We'll see a lot of those today as well. You want to use functions that are used in visualization, so making plots and all those sort of things. Once you know those libraries, and then there is this one thing here that's called object-oriented programming, which I will leave as a homework for all the people that are here in the tutorial. Just go and look this up after you're done with this entire Python session. That's today and tomorrow. It's a really, really cool thing. Once you master all these things, I want to tell you that you will be on a very good standing in terms of using Python for science. And the good news is we're going to learn a lot of these things today. Maybe not object-oriented programming, but most of the other things we're going to cover today and tomorrow. In those sessions, we will see them in action. So you're in good hands. This is a very, very good start, and it's a very good investment for your career as a scientist. So let's dive in. Okay, now, where's my notebook? So hopefully everybody has opened their Jupyter notebooks and they can kind of see these three folders. I'm gonna once again give people about 60 seconds to see if they can get here.
Thank you so much, Lordrick, for the 60 seconds. So
Mhm.
while you all are doing that, let me take a moment to welcome our fourth mentor for today. Aparajito has joined us. Aparajito will be leading the second part of Notebook 2. Aparajito, could you give us a quick introduction? Thank you for joining us.
Yeah, can you guys hear me and see me? Hello, can you guys hear
Awesome.
me?
Yes, we can.
Okay, loud and clear. Or is the audio a little choppy? Please let me know.
Okay.
Is
Well,
my audio okay? Is my
yeah,
audio okay?
yeah, it's pretty okay.
Okay,
It's a little,
okay, okay,
it's slightly choppy, but all good, all good. Where are
okay.
you
I'll,
joining us
I'll
from?
take a look. I'm joining from India. Hello, everyone. My name is Vakurajito. I work with Raja. I do some research with galaxies, and I use Python every day for my work. Um, Raja is, of course, the guy whose brainchild this program is. Yeah, nice to meet you all. I'll see you all in the second half of this notebook.
That's
Yeah.
right. Thank you so much, Paradito. Yeah, so Paradito will be picking up from Lordrick, starting with conditionals and booleans. All right, Lordrick, thank you so much for waiting patiently. Back to you.
All right, thank you. So, those who have successfully got here, you wanna there's gonna be three folders that you're gonna be working with through this entire workshop. There's a data one, which essentially has real. Oh, sorry, that was too fast. Which has real astronomical data. Let me close this again. I think I'm clicking too fast. 1 second. Okay, yes. Here inside data, we have some data files, which these are real data collected by astronomers, which you're going to be using. We're not going to be using this for the first two notebooks, but we will use it later in other notebooks to actually do actual science with this data. And then there is a plot where we're gonna be saving our plots. We're gonna making a bunch of figures to understand our science more, and they will be saved in this directory. But for now, I want you to go into your programs directory and then go into the first notebook that says Python intro. And you should see something that looks like this. Now, a quick note, if you are following along, I would like you to sometimes there's usually already solutions inside the notebook. So when I say solutions, I mean there's some answer here. So for example, you see it's already printed the word hello world here. So if that is the case for you, I want you to click kernel here and essentially just clear all outputs because I don't want you to see the answers and ruin the surprise. And so you want to clear all. So you restart kernel and clear. It will prompt you to restart here, and you will be set to go. You can see
Hello?
programming language. There's many programming language out there. This is has kind of been the classic one for scientists, at least in the last 10, let me say 12 years. No, 17 years, because it's really user friendly. It's not a super complicated language, and you can really do a lot of science with it. And if you want to read a lot about Python, there's a link here called python.org. You'll learn a lot of things about Python there. That's where you find everything about Python. And then there's a lot of tutorials, general tutorials about Python here. Oh, I actually didn't see this before. I just mentioned object-oriented programming. I didn't know it was here in the link. Yes, if you want to learn a lot about object-oriented programming, which I was just mentioning in my slides a few minutes ago, here is where you will read a lot of, yeah, it once again, the name sounds very intimidating, but it's not really. It's a great skill set to have. And then you have this thing called Stack Overflow here. That's uh that's where we go. Essentially, it's think of like Facebook, but for Python. It's where we ask and post all the questions that we have in Python, and we get to get our solution. And there's people who have used Python for long periods of time, and they'll have solutions written over there. So this is essentially where we go when we have questions about Python. You just type in your question, and there's gonna be a related question or your exact question because these kinds of issues that people get stuck with are very common, and so you'll find a lot of answers in Stack Overflow. Now, we're in the edge of AI. And so AI can be a great tool. Now, AI is fantastic. I'm gonna say that. So if at all Stack Overflow has not been helpful for you in figuring out the answers to your question, you can use AI. But I want to caution you. While AI is super useful, it can also make you not learn or not grow the programming muscles that you need. And so AI is really good. It can write you your entire code, but if you have not spent the time, if you're not put in the reps, if you're not putting in the works exactly to learn the skills, you will not understand what AI is giving you, so all the chatbots, and they make a lot of mistakes. I use AI sometimes. Sometimes I even get mad and not use it because it makes a lot of mistakes. So do not trust it completely. But in order to be able to understand what AI is giving you, you need all these skills. And so do not neglect the skills right now just because we have AI. But it can be a great tool. I can say one thing when I use AI and it's something I don't understand. So, for example, it's a language maybe I don't use, like JavaScript or something like that. I ask it to, before it gives me the code, to explain every single step. And then I will write the code on my own. That is actually a better way to use AI. So I encourage you to use AI, but be very cautious. First, learn the skills, and then you can go into AI as you may please.
Thank you
And
so
now,
much, Lord
yeah.
Drick, for
Mhm.
speaking to that point about AI because it's so very important to reaffirm how critical it is to have the foundational knowledge in order to use those tools like AI in helping with your programming. You have to know the alphabet before you can make sure that the AI is spelling your words correctly.
Yeah.
Well, thank you
Yes.
for that. I
Mhm.
actually
Mhm.
just had someone send me a quick message about using AI if we were going to demonstrate that. So we will not be demonstrating how to incorporate using AI in these tutorials. But as I was talking with Lordrick and Geronimo and Bojidara before we got started, we will be doing an overhaul of this program and in order to incorporate some new things like potentially a portion on AI. All right. Thanks, Lordrick. Please
Thank
continue.
you. Thank you. Now we get into kind of the fun thing here. That's the thing you're opening right now is called a Jupyter Notebook. You may have written down that thing in your terminal somewhere when you were studying this notebook, but I want to kind of talk about it a little bit. There are many ways to run Python, but Jupyter Notebook, especially for beginners, is one of the best ways. And that is because it allows us to run the code in pieces. And so you'll see what I mean in a second. Uh, what Jupyter Notebook essentially has is what these things are called cells. So this whole thing here is written in a cell, and this other thing here is another cell, and this is a cell. And so essentially you can run something in a cell. A cell is essentially that's a little piece of the entire canvas of the notebook where I can just run my program there and it will execute and give me what I need to see. The good thing about there are a lot of good things about that. One of them is we can add beautiful text like this. Uh, if we're doing tutorials like so, or even if when you're writing your own code, this text is super important to kind of explain what the code is doing. And let me go over this really quickly. It's super important to explain what your code is doing. A lot of the time it is for you. I cannot tell you how many times I've written code, and if I don't document well, I'll come back a few months later and I don't know what my own code is doing. And I wrote the code. And yeah, you can think like, how can I forget? When you write a lot of code, you'll forget what your code is doing. So we always want to explain what the code is doing. And Jupyter Notebooks are really good at that because we can have this kind of explanation. We can even have beautiful figures like this. But also we have these kinds of cells where we can run code. And so that is the wonderful thing about Jupyter Notebooks. So please, I encourage you to keep using Jupyter Notebooks, and then maybe with that overhaul, maybe someday we'll show how to use other things like modules and all these other things. But for now, we'll be using Jupyter Notebooks. And so let's get into it. We're gonna start with the very first thing that we do in programming, and that is using print or the print function in Python. Now, why do we need the print function? Because whenever we run code, whenever we are doing things, we want to see the results. So it's essentially like in your calculator, when you add two numbers or you do whatever you want to do, you want to see the answer. I don't think anybody would use the calculator if it does not have a screen. And so the print statement is essentially that. This is how we see what is going on. And so in any classic programming tutorial, the first thing we do is we print hello world. Now, I don't know why we print the words hello world, but it seems to be the norm. And so we're gonna go with that. And so what you can see here, if you want to print something, you write the word print. This is what is called a function. Is one of those functions that we'll talk about a little bit later. And we put parentheses in them. And in those parentheses, you see we have something written down here, which has two of these quotation marks. If you see anything that is surrounded with these two quotation marks in Python, it is what we call a string. And that will be our first data type that we are learning, okay? So this string here, we cannot print things that are not strings in one form or the other. So a string is basically just words that we see. And so we can see here we have hello world inside these two quotation marks, and that's our string. And if I run this cell now, how to run this cell? You can press Control on your keyboard and press Enter. Well, usually there's a button here. I don't see it at the moment. Move the cell up. Oh, I think they've made a new kind of Jupyter Notebooks. We used to have a play button there. Oh, or you can use this one, but this will run all. But here is the thing. Yes, the
Oh,
easiest way would be to click Control or Enter. I don't know. Maybe there's people who have used these new Jupyter Notebooks. Can I just play here? Oh, yes. Yeah, I
yes,
can also
play.
press
Yeah.
play. Yes.
You got it.
Yes, I don't use Jupyter Notebooks a lot because I use I use modules most of the time. That's why I forgot about that a little bit. Yes. But if
Perfect.
you click play here, and you can see now we have the words hello world. Okay? So great, you've run your first function. You've run your first function in Python. By the way, we can do anything else. And so let me do a little bit more examples here. And so I can comment that out. And commenting that out means we're not gonna run this line. And so you just had a hashtag in front of this line. And so we can print something else. I'm gonna copy that. Let me put something else inside the string and say, I don't know, maybe PyaR Workshop 2025. And once again, if I run that cell, I can either click play here. You see now the words are PyaR Workshop 2025. And so this is super important to be able to print. And one of those things that I was mentioning earlier about Python being the classic language for programming is you can see this is if you want to just print out something inside another language, this is JavaScript, I believe, you can see how complicated it is. But for Python, you just write print and it prints whatever you want. And that's great. And we're gonna move on to our next thing here. And so I'm gonna do this again just to keep this notebook consistent. Now, once again, this is not to say that other languages are bad. I can tell you other languages have their own kind of advantages as well. For example, C++ and Java are super fast. Java is really good when you're doing web designing. C++ is really good when you're doing some kind of machine-heavy things. In fact, Python is written in another language known as C, which was the precursor to C++. So all these other languages, it's not that they're terrible, but they can be used in other things if you want to run something faster. Now, some quick kind of things to watch out when you're doing when you're running this very first function. You can see here the format is that we have everything uh, in that string between the quotation marks. If you do something like this, okay, let me. I'm gonna try to add another cell here. Oh, that doesn't work. Let me not add another cell. Let me comment this out and show you some common mistakes that people make, which is what that note is saying there. So if you do this hello, and then you do this world, you put each one in its own quotation mark, that will give us an error. Oh, did not. Oh, but you can see it kind of not not the exact thing that we expect.
Exactly. Yeah. It's
Yeah.
missing
Mm,
that space there.
mhm. And yeah, and those are kind of the kind of things that I think with experience we're gonna see a lot more of these of these kind of things you wanna. But this is not the correct quotation way to put it. I think you wanna put it like this. Anyway, that was just the thing here they were telling you to watch out for. Okay, I'm gonna move on from this cell now. Once again, Python is not only good for just printing out your strings, you can also do a lot of math. You can essentially just use it as a calculator. And so the way you would do that is just writing in your cell, your normal, this is an example of an addition function. So you can just add two numbers here. And if you run that cell, you'll get 4, which is what we expect. And if you do 4 minus 2, exactly what we expect, you'll get 2. And then if this is 4 times 2, where you use the star operator inside on your keyboard, and I don't think there is an actual times operator, but you can use the star, and that should give us 8, which is what you expect. And then you can also do division. This is super straightforward things that you can do with Python, but it's wonderful. And sometimes we want to do this maybe in a super complicated numbers where you can add and divide and do all things. I will talk about the we used to call it BODMAS, but I think people call it PEMDAS here. Yeah, where I learned in in a British system, so we call it BODMAS. But yes, I think what is it called here? PEMDAS?
Yeah, it's
Yeah,
different in
yeah,
different regions. Yeah.
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 Yeah, I think
I
it's
was
PEMDAS. Yeah.
also yeah, I was
Yeah.
also taught under the Bottomless system. So
Yeah,
yeah, it's the same
yeah,
thing.
yeah. Anyway, we'll get to that. So this here is an important function where instead of having one of those star operators, you have two, and so that essentially just gives you a power. So this is 4 to the power of 2, and what do we expect for that? We expect that to be 16, and so that is great. Just another word of caution: you don't want to do this. Let me see in a lot of other languages probably and in I think other writing languages people write a power like this. If you do this you get 6. Now that looks like it added the two numbers but not really. This is for what is called a bitwise operator. I am not going to get into that because I don't want to get into analog and electronics and all these things, but essentially you don't want to do this for 4 power 2. You want to do the two star signs and that should give you 16. Okay. And yes, that's what that note here was about. And then here you wanna follow once again the PEM. I hope I'm saying the correct thing, PEMDAS, but if you're not familiar with that, it's just BODMAS, which is essentially saying that you wanna do it's gonna open the parentheses first and then it's gonna work on, let me see, bracket opening and then dividing and then multiplication and addition and then subtraction. So it's gonna follow those mathematical rules. And what do we expect for this here? Oh, sorry. I used to be a teacher, so I am kind of expecting the kind of feedback from students, but I'm just realizing now that that's not gonna be super super easy. But
Yeah.
yeah.
Everyone can the chat is open for everyone, but please, yes.
Mhm.
I was a teacher for 13 years also. I definitely understand that. And I really appreciate that you're bringing that here to
Yeah.
us. But yes, people can are only able to respond in the chat.
Okay. So if we run this, what do you expect? So if you open the bracket first, you'll get a 3 here, and then this will be 3 times 3 to the 4. I believe we do the power first and not the dividing first. Bod mass. And so that 3 to the 12, the 3 to the 4 is I don't know what 3 to the 4 is. We can do that on the side. I forgot how to add more cells. Let's do this.
You can just highlight a cell
Mm.
or like click to the left in the white
Oh,
space area. Yeah, yeah.
oh, okay.
Or
That
also,
works. Or
Mm.
you can
yeah,
just hit B
Mm.
and
Yeah.
just hit the B key.
Okay. Thank you. Yeah.
yeah.
3.
And I also like the quick like shortcut to do escape
Mhm.
A. Like if you hold escape A, it usually.
Oh, nice. Okay, cool. Yeah, I think I just tried that. So you click a cell and I press A and it just works. Oh, okay. But I don't know how to delete them now. Anyway, we'll just keep them here in my computer, I guess. So 3 to the 4 is
Deleting
zero.
is just,
Mm.
sorry, deleting is just D twice.
Oh, that did not work for me for some reason.
Uh, quick
I think,
succession, D, quick
oh,
succession. Oh, I
yeah,
think
it
it's,
did.
I think it's clashing with Chrome's shortcuts.
Oh, okay.
Oh, that's
Yeah.
right.
Yeah.
That's the Chrome. Yeah, there's issues.
Okay, yeah.
You got it.
Now,
Okay.
now I lost the entire notebook. Oh dear. Okay, we can restart the cells here. We clear all the answers. Don't worry about this. Okay.
Also, I should take the opportunity to remind everyone that the order in which you run the cells matters, because Python will remember, or rather Jupyter will remember.
Oh, okay, yeah.
So yeah, if you go back and run earlier cells again,
Mhm.
know that it will overwrite anything, any variable names, etc.,
Yeah,
that you might have defined below. So you'll have to run it again. Um, anyway, uh,
in series,
over and
exactly.
out. Yeah.
Yeah. Yes, thank you, Parajito. I was gonna try and mention that when we start doing the variables.
Yes.
Yes, thank you so much. Yeah, that is a good thing. So if you run something here, Python is gonna remember this answer. So you wanna run the cells in order. Okay, so we're not gonna be deleting cells, apparently. So we have 81. So remember, we opened the bracket. It was 3 times 3. So sorry, it will be 3 times 3. And then here, oh, it won't be times 3, sorry. We're doing 3 to the 4 first. It will be 81. 81 divided by 5. That's 16.2. And so we have 16.2. And so we have 3 times 16.2. That will be 48.2, I'm pretty sure. Let's just do that here. Oh, I did it above. Anyway, so 16 times 3 will be 48. Sorry, 16.2 times 3 will be 48.6. And then once you take out 6, what do we expect here? 42.6. So you can see the way it followed the orders of operation there. And so you want to keep that in mind whenever you're doing math in Python. You wanna make sure that you should know that it's following BODMAS rules, and you should write your expressions accordingly. Okay, it's great that we can use Python as a calculator like this, but sometimes you want, or at least most of the time when you're using Python, you want it to remember what is some number, you want to reuse maybe. Maybe you are multiplying the mass of something, and so you want to set the mass that to equal to something. And so that is when we use these things called variables. And so in Python, now this is one of the quick things also one of the first things that you want to understand. This is where things kind of differ with math. This sign here is not an equal sign. I mean, I know it looks like an equal sign and you'd probably call it an equal sign, but it's not an equal sign. This is an assignment operator. What this means here is not A is equal to 1. It means I am assigning A, the variable A, to be 1. I'm going to repeat that again. This is not A is equal to 1. I am assigning the variable A to be 1. And here I am assigning the variable B to be 2. Now, you can use whatever variable names you want. You can use logic. You can use your own name. You can use, whenever you're doing science, for example, you are calculating density. So you let something is equal to mass and something is equal to volume. All those variable names are allowed, okay? But if you want to assign them to a particular number, that's when you use this equal sign. Here it's used as an assignment operator. And now, to show you that that is in fact the truth, let us print out those two things here. So here we are printing A, and here we are printing B. And so once we run that cell, you can see here, this print A statement gave us the 1 here. We assigned A to be 1. And then this print statement here, we are printing B. And so this is a kind of
Um,
another thing that you
so
want to notice here.
so sorry.
Hmm.
So sorry to interrupt, but Lordvik, could you zoom in a little?
Oh,
I
okay.
think it will be better for the recording because some people have smaller screens. Yeah, this is
Okay.
perfect.
Is it
Thank you.
better? All right. Thank you
Yeah,
so
yeah.
much. Yeah, I didn't realize that. Yeah, I'm okay. That was a little small. Okay. Hopefully this is better. Okay, once again, we've print A and we've print B. Now, another thing I want you to notice here, super quickly, is that we don't have to use print function just for strings. We can also print variables. And so you can see here, this inside is not a string, it's just the number A. But we want to see that answer. And so, once again, we can kind of expand this a little bit. Maybe we want to do math and we want to assign that answer in some variables. And so here we have assigned A to B plus 2. And so when we print A here, what do we expect? We expect that it will print the number 3. Now, an important thing here, once again, Python reads line by line, and so we can reassign that number. Let's say we don't want it to be the result of 1 plus 2 again. We want it to be something else, maybe 27. We can reassign that. And if we print A again, we should see two different things. And so one of them is that A is equal to 3, and then A should be equal to 27. And so this is to show you that we can, in fact, reassign the variable A. Okay, we can also perform things inside the print function. And so here we are reassigning A. Remember, A was 27 right now. If I print A, sorry, if I print A right now, it will be 27. That's one way to print A, but I don't advise to do that. Let's do this instead. If we print A right now, it's 27. But now we are reassigning A to be 1, and then we are reassigning B to be 2. And so what we expect here is that the print function is going to give us 3. Okay, once again, we can use the comma separated inside the print function if we want to print more than one thing. And so if we print A comma B here, what do we expect? We know A is 2 and B is 1, and so we expect to get 1 and 2. And so here we get 1 and 2 separated by the space. This is just another way you can use the print function. And so, kind of one thing you also wanna be careful about is that a string will be printed as is, but operation will be performed on variables if those variables are indeed numbers or they're in strings. We can see operation with strings in a second. So if I say print and then I put quotation marks 3 plus 4, Python is going to take this string as is. It's not going to add those two numbers. And so if I print, it will just print the string 3 plus 4. And so that is the thing they wanted you to watch out for. Okay, let's work a little bit more with variables. Python has some of these wonderful shortcuts, and you'll see this a lot in when you're doing loops. Sometimes you just want to add 1 to the number. Okay, so first we reassign, let's say we reassign A to be 1. Okay, and then we just want to add 1 to that particular number. Sometimes I don't remember what the variable is. I just want to add 1. This is a way to do that. You just write plus and equal signs. This is the same as writing A is equal to A plus 1. Once again, this is kind of where programming differs with math. In math, this would be an equation with no solutions, but this, once again, in Python is not an equal sign. And so what do we expect? I would love to see the chat here to see what people expect with this thing. But essentially, what you expect is that A is 1 in this case, and so 1 plus 1 should be 2. And so we expect first to print 1, then to print 2 for this amazing operation here, and then A star equal 3. This means just A is equal to A times 3, and so this should give us 6. And exactly what we expect. And you're gonna see a lot more uses for this kind of notation when you're doing loops. Okay, this is another fun thing that we can do super quickly. We can do a lot of other things with these things. Now let's get into the data type called strings. And so here we are assigning this variable s, which makes sense because we're working with a string, to this string here called hello world. Okay? And so here, I'm gonna comment this out in a second so that we just see what happens there. So if we print S here, we should see hello world. Nice. Okay. So this is now, we can assign essentially anything to be a variable. You will see in the future, we can even assign a function to be a variable, and that works out just as well. And okay, so you can see here there is something written as dot lore. Okay, this is another one of those functions, but this is a special kind of function because it's working on this string. Now, once you get into the depth of object-oriented programming, you'll learn that this is in fact something called an object. The good things about object is that we can also work on those things. And so this thing here called lore is essentially gonna work on this object here known as a string. And this is essentially just gonna turn every word that's in uppercase to be lowercase. And so let's see if that is the case. So you can see the first statement here, print S, should print the same thing as hello world, but s.lower should make the H and the W lowercase. And exactly as expected. You can also do that for uppercase, so sometimes you just want everything to be uppercase. So first we're printing S, and then we're printing S lower, and then we're printing everything in uppercase. Amazing! Okay, we have hello world in uppercase. We can also replace words. And so here we have s.replace, and this is essentially saying replace the word the first variable in this function here. So we can also add things inside functions. We'll see a lot more of that later, but it's saying replace the word world, which is the first thing here, with the word zip. Okay, let's see if that works out as we expect. Exactly. So you can see here the word world has been removed and we have replaced it with the word zip. And this is the point where I encourage everybody just play around with these functions. Play around with this is how you kind of learn. And to me, it's kind of fun as well. Just play around a lot with these functions and you can make them do a lot more things. The good thing about programming is that different people come up with different things and they make a lot of beautiful things. So as I was mentioning earlier, you can do operations with with strings. So here I have s. Uh, we have assigned s to be hello world here, and we are gonna add hello world. It's a beautiful day. And so we have made a new variable called newString. We're gonna print this variable called newString, and newString should essentially be hello world, and it's a beautiful world. Okay, I'm gonna comment out this second one first so that we can see if that's exactly what to expect. Oh yes, it is exactly what we expect. We can also multiply strings. Okay, so this will be hello world times 2, so it should be hello world, hello world. Let's see if that is the case. Yes, that is indeed the case. It is hello world, hello world. Amazing. So we can do math with strings. Practically, I don't know if I've done this a lot. I've only seen kind of the seed in tutorial, but I don't know. Maybe you'll come up with a program that needs to multiply some strings. So go for it. All right, and now we get into another data type. I'm gonna take 1 minute here just to kind of people to absorb what I just said so that I can get into data types, into other data types.
And we have 5 more minutes for your section, Lordrick, to take
Okay.
list and tuples, and then we'll be ready for a PyR 2.
All right, so we only have list and tuples left?
Yes, the PyR is going to pick up with conditionals and booleans.
All right. All right, that's amazing. Okay, so I'm gonna try to go through this quickly but concisely as I can.
I think
Yeah.
you can keep the sorry, you can keep the tuple section brief because I don't think we use
Tuples.
tuples in the
Ah,
later notebooks. So yeah, just to introduce it. So
yes, I think I can just quickly
yeah,
just
yeah,
kind of introduce them in a way. But lists are
yeah,
like super important, so
yeah, absolutely.
yeah, we can go. Okay, let's get into lists. This is an important data type because sometimes we want to store data types into other data types. And I mean, not just that, but we want to store, essentially, you just want to have a list of things. And a list here is just essentially the same as your list of groceries. It's just a list. It's just a list of things. And so we can have a list of strings. We can just have a list of numbers. Now, one quick thing I want to mention here, in Python, there are different types of numbers. There are what we call floats, and then you have ints or integers. And basically, integers just don't have a decimal point, and floats have a decimal point. And these kind of behave a little differently. I'm gonna leave that as a homework to the beginners here. Just kind of go and see those differences. But it's important to know that in Python, we essentially don't just say numbers. So, for example, here I would say I have a list of integers, or a lot of people you hear them say I have a list of ints. And so let me comment this out. So here I am saying I'm assigning the variable x to this list of integers here. And so let's print that out and see what happens. Oh, exactly. Now, what I want you to notice here is that a list is just made up of whatever you want in the list, and you want to put that inside square brackets. This is very important. A list is square brackets. Now, you'll learn other data types when you keep going. For example, tuples or tuples, however you people pronounce them, they are put in parentheses. There's, for example, dictionaries, which I use dictionaries a lot. These are great data types. You should definitely learn those sometime after we finish this workshop. We put those in curly brackets. But for now, we're learning lists, and so I want you to keep this picture of square brackets in mind. So when we put anything in square brackets and we separate it by commas, that in Python is what we call a list. Now, why are we so hyped up about these lists? Is that we can do a lot of things with lists. So, say I just want this number. I just want to get this very first number. Now, here's another important thing in Python is that Python is what we call a zero-indexed language. A zero-indexed language means we don't count things from one as one would in normal life. We count things from zero. And so this first item here in your list is not called the first item. It's called your zeroth item. And then the second one is called your item in your first item, or your item with index 1. And then you'll have another item with index 2, and then you'll have another item with index 3. And so let's say I just want this first item, which in this case, it's 0. And so if I print x and then I print x of 0, I should expect just a 0 down there. And that is exactly what we expect. And so this is not the only thing I can do with this is not the only kind of list I can make. Let's make another list. Let me call it J. Okay, just another variable. And let me copy this. And let me put that there. And let's say this first things, I don't even want it to be an object. Let me make it a name. Let's say Lodric. And then I want us to print the very first item in that list. So we want the 0th index. I also put that. So another thing that you can kind of notice here, when I'm indexing, this is called indexing. You refer to the index, you put it in square brackets. And so I want the 0th item. And so if I print, what do I expect here? I expect to see the string Lodric. That is indeed what happens. And so if we come back to this cell here, we can print the first item, which will be 1. Okay. Great. So 1 is printed there, and I can also show you the other items here. Great. So this is how we index. So we can refer to any item in the list using just this indexing method. And list can be as long as you want. List can have 1,000,000 items in there, and it can have 1,000,000,000. And so what happens? Before I get into that, how do you know the length of the list? Essentially, how many items are in the list? So I can just try to print here. And this is once again the print function. You can see here we have one string that says length of, and then we have comma length of x. This is one of those wonderful ways we use comma inside the print functions. You can see we want to print a string here, and we want to print the length of x. And so to print the length of x, we use this function called len. So you just write len. Remember, x is this list. How many items are in here? 1, 2, 3, 4. So what we expect here, it should say the length of x is 4. If it's not 4, I will be very sad. It is indeed 4. That's great. So that is how we know the length of a list. Once again, a list can have any length, as I mentioned before. But if your list has, I don't know, 300,562 items, and you just want the last item, you're not gonna have to write 3,562 here. You're just gonna write minus one. And so this minus one index is essentially just the very last index. And you can kind of imagine minus two index will be the second last, minus three will be the fourth last, will be the third last, and then minus four as far as first. So what do we expect here? At least I expect to see 3, 2, 1, 0. Let's try that. Amazing. 3, 2, 1, 0. So we can index a list essentially from the end of the list just by using negative indices. And now, another thing that we can do with lists uh, is called slicing. Now, say I want more than one thing inside the list. I just want a couple of items. Let's say I want, so this is called 0 up to 2. Now, here is another important thing. So let me first comment this out. And oh, I wish this was a classroom so that I could do this in front of class and just ask, what do people expect here? Anyway, so this is the zeros index to the index number 2. Now, I know, at least when first I saw this, I thought maybe I'm gonna get the zeroth index and the first index and the second index because it's saying 0 and put a colon here. This colon just means all the way to 2. I was like, oh. But then Python is what we call an exclusive language. It includes the lower index, but does not include the upper index. So this is the lower index. It's just some more terminology I'm throwing at you, and this is the upper index. It does not include. So essentially, this is saying giving me everything from 0 all the way to 2, but not 2 itself. And so what I expect here is just to see 0 and 1. Okay, let's see what happens when we do that. Oh, amazing. So we have this is why it's called slicing because it means like we're slicing the list essentially. We're cutting it into a piece. And so yeah, once you can see that we can try that. Okay. Now if I want all the way up to the second index, so I'll say from 0 to 3. Okay? Remember? 3 is gonna index the fourth item here, and 2 is indexing the second item. But we don't want the fourth item. We want all the way up to the third item, which I think maybe kind of makes sense that we just want third item. So it will have from 0 to 3, and sometimes you don't want to write the 0 here. You can also just put a colon here and tell it to go all the way to 3. It is the same as it will when Python sees this, it just assumes that the first index is indeed 0. And so we should see the same thing. Amazing, we do see the same thing. And so maybe sometimes you want this is kind of just this is where I encourage students to just go and play around. Maybe sometimes you want 1, and then if you don't put anything in the upper index area here, it's just gonna assume you want 1 all the way to the last index. So I should expect to see 1, 2, 3 here. Amazing, we do see in 1, 2, 3. And then you can also, play around even more. You kind of be like, I want from so once again, when you don't put anything here, it assumes this is 0, but this is essentially going from 0 to the second last item. This is when you're being very, very fancy. And let's see, what is the second last item? I forgot where the list is. Yes. So, let's see what happens when we do that. Amazing. So, the second last item here was indeed 2, but once again, Python is upper index exclusive, so it won't give you that second last item actually, it will give you the one before that. And so that's this is what you get. So you can play around with that as well. And this is one of the you can see like here I'm just having fun putting indices, but we do this a lot in programming. We do this a lot when we're working, especially when we're doing linear algebra or something like that. We do a lot of indexing, and I think at some point maybe you will learn about arrays where they can be two-dimensional lists with one data type. But I don't want to get into that at the moment. But we do a lot of indexing and a lot of slicing. And so here's another fun thing you could do. We have our list here. We have we have now reassigned x to be the list 1, 2, 3, 4. If you print that, you'll get 1, 2, 3, 4. But let's say we want the ones index to not be 2 anymore. This is the number in the ones index. Once again, be very careful. Python is 0 index, so this is the zeros item. This is the ones index. And so we want that ones index to not be 2 anymore, to be 486.1. This is an interesting number. I don't know why this one was chosen. But yes, let's try that. When we print, you can see here the first time the x used to be 1, 2, 3, 4. But once we replace the second number, which is index number 1, to be 486.1, you can see the second item, the second x is now 1, 486.1, and 3, then 4. Okay, lists can hold a lot of things. I think I've said this. I've shown this in my example implicitly there. You can also put a string inside a list. But here is the crazy thing: you can put a list inside a list, and it will still work fine. So here we are assigning a, the variable a. I believe last we had of a, it used to be 1. Let me see if that is the case. Oh, it's 6 now. Okay, yeah, I think we did print, we did a is equal to a times 3 or something when a used to be 2. A used to be 6. And now we are assigning a to this variable here, okay? And so this variable will be the list that has the number or the integer 1, and then second is a string, and the third index is a list. And so let's see if we can see that before I get into this. Okay, it is indeed A is now indeed a list. This is the first line here. It's the first line here, and we can index the first item, we can index the second item, we can index the third item. Now, here is where Python gets cool. We can index something if it's a list inside a list. And so here you can see this last line here is saying that inside A, give me the third item, which is an index number 2. We know that third item is a list. Inside that list, give me the very first item in the zeros index. And so what do we expect here? The last print statement should give us 1, and voila, we have 1. So this is one of the cool things about Python. All right, so maybe you're like me and you're lazy and you don't want to write your lists in 1, 2, 3, 4. We can use functions. And so before I write that, let's see what this range function is. Let me print, should I print range? So this range function, how people use this is where you want to start, okay? You want to start with the number 1, and then the second number means we are ending here. Remember that Python is an upper index exclusive language, so this is not going to end in 10, it's going to end right before 10. But you can see here we have something else here, and I'm going to let you guess what you think this other thing is. Oh, but before that, okay. Let me just print the list so that you can see what I mean, and then we can talk about range later, that cool function there. Let me print this list. Now, another thing here. Oh, that's why what happened I didn't expect. We have to make it a list. Okay. And so here we have, if we want to make anything a list, so here range is just a function. I think I'll let the parameter, maybe we'll talk about functions a little bit later. But we can make anything a list, okay? The output of this function will be this list here. And if I print that list, it gives us the number 1, 3, 5, 7, 9. And so if you notice very quickly here is that what this range thing is doing here, oh, sorry, my Grammarly is getting in the way. What this range thing is doing here is essentially saying that I'm gonna give you all the integers starting from 1 all the way up to 10 in steps of 2. Okay? And so that means it starts with 1, 1 at 2 is 3, 5, 7, 9. And so you essentially get all the odd numbers. And so we can do this again. Let's try to print a list. I'm gonna be fancy a little bit here. From range, let's say 1, no, let's say that with 2 to 10 again in steps of 2. What I'm expecting here is that I should get 2, 4, 6, 8. Remember, Python is upper index exclusive, so we won't get 10. Let's see. Oh, oh, okay. I haven't finished my brackets there. Okay, and this is a good point to tell you.
Yes.
Errors are not the word. Don't be scared of errors. Okay? In fact, most of your life when you're writing code, you will get errors. Okay? Don't worry about them. You just have to understand them and fix them. For example, this error was literally showing me that there's something missing here. Okay? Which means I have to add one more bracket. So do not be scared of errors. Okay? I can't believe it took me this long to mention this. Do not be scared of errors. Errors are great. We just fix them. And actually, most of the time in writing code, you will get errors until you don't, then you are done. Okay? Basically, what we do as programmers essentially is just solving all the errors all day. And so if we print this, oh, it's still saying that I don't have enough. Oh, I still need one more bracket. Amazing. Okay. And so now we've added one more bracket. That should work. And so here we have our list as we expect. And so there is other fancy ways. Here you will just, if you do range of 5, it should give you 0, 1, 2, 3, 4, 5. It will assume all the other things. It will assume you're starting from 0, you're ending at 5, and then it will assume a step of 1. And so if we print y, where you're saying y into the list of it, it should be 0, 1, 2, 3, 4. And so let's see that. Amazing. Okay. We can add we can add two lists together. And so remember, y is 0, 1, 2, 3, 4. And then where is x? X is 1, 3, 5, 7, 9. When we add this together, it's not going to be what you expect. Let's see what it is. Oh, it concatenated the lists. Okay. Later you'll learn about another data type called an array, which will do what I think what probably most people would expect is that it will add these numbers together. That means to add the one to the zero and the three to the one, all that type. But for lists, when we add, it concatenates. And so once again, much like a string, we can also multiply lists. And so this should give us the list y twice. And so if we do that, that is essentially what happens. Okay. So we can assign the variable as well into another variable to be an operation of list. So here once again, when we add x plus y, it should be this thing. And if we print, we can print that. And then there is this sort function, which is another funny thing I'm gonna mention very quickly here, is that we can arrange the numbers inside a list. And if we print that, it should give us that very same list, but now arranging the numbers in ascending order, which is a great thing we can do with lists. We can also add things to lists. These are some of those things which I want you to I'm just introducing to you, and you can just have fun with them by yourself. Okay. And so here, essentially, we have a list called x. We assign the variable x to the list 3, 2. And so once I append 1, I should expect the list should now be 3, 2, 1. And then I can append 0 again. Let me append 1 first. Okay, so now you can see we print x, and x is 3, 2, 1. But we can also append another number, 0, and it should be 3, 2, 0. Okay, I know that was a lot of information, but don't worry about it. Once you start playing around with the notebook, it will be super, super, super clear. And now, very quickly, I'm gonna mention something called a tuple. This is a lot like a list, uh, except the first thing is that you put it in parentheses. And the second thing is that we can't change things inside a tuple. Okay, so it works a lot like a list. For example, here, if we print letters, it will be the list A, B, C. Sorry, not the list. Sorry, the tuples A, B, the tuple A, B with the elements A, B, C. And once again, we don't call these items inside tuples. We call them elements. And then, if you want to refer to the second element, this is I'm just using it the same way we do with lists in square brackets, and you'll get this second element. But if you try to change something inside a tuple, let me try letters. Let me say I want to change that B. Sorry, the second element B to be something else, to be baby. Let me put it in a string, baby. it will tell me, no, 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 no. You're not allowed to do that. You're not allowed to change things inside a tuple. Now, tuples, they have their uses, but I'm gonna table that discussion in Slack or whatever else you want to ask me. And so, feel free to ask me any questions you want. If there is something that I went over too fast, there probably is at the end there. Feel free to ask me all the questions in Slack. But believe me that once you start running these notebooks, it will be extremely clear. And I know I've gone over time. I'm very sorry, Jamaica. But yeah, please take over.
Thank you so much, Lordrick.
Mm,
And yes,
mm.
we are not using Slack because everyone can't get on Slack. So again,
Oh,
questions and comments, please put them here in the Zoom chat. And thank you so much, Lordrick. Lordrick will be here for the rest of the session. So if you have questions about anything that he went over, please put them in the chat. I'll also make sure that everyone gets a copy of the chat transcript with all the answers in there as well too. All right, Aparajito, we're ready for you to pick up with conditionals, booleans, loops, and functions, and we can leave out importing other modules, please, Aparajito.
Sure, sure.
Thank you so much.
Can you guys hear me better now? Am I audible, loud and clear?
Yeah, loud
Are
and
my
clear.
words cutting off the ends of my words or anything? Okay, great,
Not at all. Sounds great.
perfect. I think I just had to adjust the noise gate for the Zoom thing. Let's see. Yeah. Can you guys see my Chrome window now?
Yes.
Okay. So we studied a lot. We learned a lot. We learned about the basics of Python, using Python as a calculator. We learned that Python can basically work with numbers and it can work with more than numbers. It can work with strings, right? Strings of characters. And then you can put some of those things together into lists. You can make a collection, like a list or a tuple, and you can manipulate those collections, right? So those are the basics. But so far, we kind of have something that's a glorified calculator and something that prints some words, right? How do we use these things, right? So far, we haven't really done much that your calculator cannot do. Obviously, there's the printing stuff, but how do we use it practically? So to get there, we will get there in the later notebooks, but there's a very, very good reason to use a programming language, right? And that is that you can make things. You can make things according to your own needs. You can customize functions, right? Calculators come with a fixed number of functions. You can, unless it's like a scientific calculator, you can't really define your custom functions. And even then, there are limitations to what you can define, how much data you can work with at a time. So a programming language on a proper computer gets over these hurdles. And to get there, the next stepping stone is to ask, what do we do when we need to repeat some code, right? So far, we have written some blocks of code. We have written a little expressions. We have done our little assignments. We have run our little functions. But sometimes we need to do this over and over again, right? Now, there are two kinds of ways when it comes to repeating things, repeating a block of code. One could be repeating the block of code over and over again in the same place, right? So say you have to run the same function over a complete data set, right? Over a full data set. So you take every element of that data set, you throw them all in a list, for example, and you run that function on every single element. And you can do that in one place, right? Or you might need to run a block of code at some point and then do some other stuff and then come back to it and do it later, right? And besides this repeating, there's another thing, which is decision making. You may write 2 blocks of code and you can tell the computer to run one piece of code if one condition is met and run a different piece of code if a different condition is met, right? So that's where the conditionals and booleans come in. So we've learned about a lot of different data types, and we've learned about integers, floats, lists, strings. Now we're introducing something called a boolean. If you have learned about, if you know the basics of computing, you know booleans are the most fundamental variables. Everything is a 1 or a 0 in a binary computer system. So as you can see, there are 2 variables here. One is called true, and the other one has been assigned false. And you can see that the T and the F are capitalized, and they are highlighted in green because Jupyter recognizes the syntax as Boolean. So what does it give us if, say, okay, so I'm just assigning it at first, and then what happens if I print A and B? All right, so A and B would be true and false. What does that give us? Obviously, false, right? True and false is A and B. A and B is in true and false. It gives us false. What happens when we do A or B? Obviously, it should be true. Does it give us true? It does give us true. And if I print not A and not B, what should it give us? Not true and not false. So it should give us false and true, right? Does that work? Okay, it works, right? So these are Boolean variables. There can be only 2 possible values, true and false. And Python has something called a soft data type. Soft type setting. We don't need to get into that. Suffice to say, these are Boolean variables, and you can do Boolean stuff with it. You can do Boolean operations with it. Numerical comparison. We have learned about assignments using the equal sign. Now, what does it mean when what do we do when we have to compare things, right? So you can see that we have used something that's completely unnatural in regular mathematics, which is 2 equal signs back, right? What does this mean in mathematics? Nonsense. But in Python, it does mean something. It is basically asking the programming language, is the thing on the left side and the thing on the right side the same? Are they equal? Okay? Are they equal? And the first one, obviously we know 1 is not equal to 2, so it should give us false. But the second one, you can see that it's an exclamation sign followed by an equal. Okay? Exclamation sign equal. Once again, nonsense in regular mathematics does mean something in Python, right? What does it mean? It is asking, are the 2 things not equal to each other? So we know 1 and 2 are not equal to each other. So that means it should give us true, right? Bingo. Okay. We are doing decision making. We are setting things up. Obviously, then we have something that is familiar in regular mathematics, which is the less than sign and the less than equal sign. And similarly, the greater than sign and the greater than equal sign. We know 1 is less than equals 2, and 2 is greater than equals 1. Anyway, I'm going to skip over that. Shamika, how many minutes do I have?
We're already at the time for notebook 2, but let's take another 10 minutes because notebook 3.
10 minutes.
Yeah.
10 minutes. Okay. I'll try. Give me a 5-minute heads up, will you?
Will do.
Okay, thank you. So, okay, moving on. We are trying to introduce something called if-else statements. Okay, we know how to compare things, but how do we tell the computer to do one thing if one condition is met and another thing if another condition is met? And that's where if-else statements come in. So, how does an if-else statement work? We have defined a variable called x, and then we use the if statement. If a condition, we have defined a condition, is x greater than 10? If it is, then it will do this thing in the indent. Okay, you can see that there's an indent. There are 4 spaces here. Okay, or tab, or a whole tab, or 4 spaces here. Okay, and then we do else. Else is for when that condition is not met. If this condition is not met, okay, that's when this thing happens. Okay, 2 options. Either the condition is met, in which case this thing happens, or the condition is not met, in which case this happens. Okay, and remember, you should keep these indents consistent. You can do 2 indents. Okay, I can introduce another tab. It's fine. You can indent with only a single tab. Only a single space instead of 4 spaces. I don't like that. I think this looks cleaner. Okay, a tab looks cleaner. But anyway, we know x is not greater than 10. Okay, x is 5. So this condition won't be met. And instead, this will be printed. Does this work? Yes. It says x, in this case, which is 5, is less than or equal to 10. Okay, that's what it printed. Now, if I turn this into 15, you can see that the first condition is met, which is why it will print the first statement under the if statement. Okay, again, be careful with your indents. Doing this is fine. And it will work unless you have something inside the if-else statement. You can nest if-else statements, which is which we're going to get to next. And in that case, indents are actually very, very important. Anyway, so we are going to introduce something else called if-else, which is concatenated into a single statement called elif. Sorry, not if-else, else-if. Okay. So whatever you want to check 2 different conditions. If condition is met, then it prints something or it does something. If condition is not met, then and only then it checks another condition. Okay. And if that condition is not met, it can move on to a 3rd condition, or it can go straight to the else statement. Okay. What if we want to do that? That's where elif comes in. We don't do another if statement, we do elif. Okay, so we have done x equals 10, we have assigned x equals 10, and this one condition for if x is greater than 10, this one condition for when x is greater than 0, and another condition for when neither of those conditions are met. Okay, so if I run this, you will see that x equals 10 is met. Sorry, x greater than 10 is met. So x greater than 10 is not met. That's why it goes straight to this, right? The second statement. It does not go to this, and it skips over this. It meets this condition, but it does not meet this condition. It does not meet this first condition, and that's why it moves on to the second condition, right? It prints whatever is here, right? X is greater than 0 or less than equals to 10, okay? What if I change it to 100, okay? Then the first condition will be met, and you can see that it doesn't go to the second statement, okay? It stops there. The first condition is met, so it just stops, okay? What if I do 0, okay? See, it went to the last statement because neither of the first 2 conditions were met. So using elif, you can check conditions in sequence. Jamika, is that 5-minute warning?
Yes, sir.
Okay, great. We're doing good. Right. Next is the loops. So you have to establish how to tell the computer to check for a condition and do 2 different things or 3 different things. And now we're going to look at something called loops. I'm going to skip over while loops. While loops are almost never used, and we don't use it in our notebooks. And they're kind of dangerous. I don't like them. So moving on, we're going straight to the for loop, which is the standard loop everywhere. Okay. So we have defined a list. My list 0, 1, 2, 3, 4. 4 elements, right? There are 4 elements in that list: 0, 1, 2, and 3. 4 numbers, 4 elements. And we are defining a list. We are saying for I is a placeholder variable. You can see that we have not defined a variable called I, right? We have not defined a variable called I today at any point in this notebook. But we can use it here because for loops are special. Whatever variable name you use here, it doesn't have to be defined anywhere else. The moment you tell Python this, you structure a line of code like this, Python knows that I is supposed to be a placeholder variable. I is supposed to be the variable that the for loop uses to iterate over a collection. Okay? So it says for I in my list, so if I is each single element in this list that I've defined my list, print I. Okay? So if I run it, you'll see that I is printed 1 by 1. Okay? My list, every element of my list is printed 1 by 1. The loop loops over the first time, it iterates the first time, it catches the first element. Okay? It picks up the first element of the list, prints it, it iterates the second time, it picks up the second element of the list, prints it, and so on and so on. Okay? Until it has run out of elements, and then it just stops. Okay? Safe and sound, nice little loop. What's the format? For a placeholder variable name in a collection name colon, and then indent, and then put whatever you want to do inside the indent. Okay? Now you're going to see why indents are so important, especially in loops. Okay? You can see that if I run the exact same thing and then I put something outside the indent, so if I don't indent this last line with a tab, then it will the loop will run over only this statement and nothing below. Okay? If I put the statement inside the indent, can you guess what will happen? Obviously, it will iterate over that statement every single time, and it will print all done 4 times. That's what happens. Okay? Anything that I don't want repeated goes outside the indent. Anything that I do want repeated goes inside the loop by putting it inside the indent. I think we're coming up on the time. So I'm just going to show you a nested loop. As you can see that there's one for loop, and then there's another for loop inside it. And you can see that there are 2 levels of indent. So this is one level of indent. Okay, inside. You can see that whatever goes on in this inside loop, okay, this statement is repeated every time the inside loop iterates over the j variable, and this thing is repeated every time the outer for loop iterates over the I variable. And not only that, this entire inner loop is iterated every time over I variable. Okay? We learned about range. Did we learn about range? No, this is the very first mention of range. Sorry, I'm just going to steal 1 more minute.
Yeah, go
this
ahead,
always
please
happens
do.
with notebook 1. Okay. So range is another collection. It's kind of like lists and tuples, but it's defined succinctly. Range just means a collection of, let's see, until just open a new cell and to show you range 2 will just show up as a range 0, comma 2. Okay, so I have to convert it into a list. And you can see that is basically equivalent to counting up from 0 to right before the end element. Because just like indexing with lists, it starts before the final element. Okay? And a range basically has 3 parts. I'm going to go with 6 and this. And once again, we can convert it to a list. You can see that a range is composed of 3 arguments. The starting point, the end point, exclusive. So the end point won't be counted. It will stop right before it reaches the end point. And then step, okay? So it counts from 0 to 6, excluding 6 in steps of 2, okay? That's what it does. You can get rid of the third element. You can just work with 2, okay? You can work with 2, and the default step will be 1. You can get rid of the first element, and you can just work with 1 argument. And it will assume that the starting point is 0 and count up to right before the argument, okay, in steps of 1. Or you can work with 2 arguments and set a custom starting point, and it will start counting from 1 instead of 0, okay? So that's range. This is a nested loop. So as you can see that the outer index changes from 0 to 1, and the inner index changes from 0 to 2, okay? So outer index 0, outer index 0, 0, 0, and outer index 1, 1, 1, and this should be inner index, okay? And you can see that outer index 0, okay? This whole loop, inside loop, ran 3 times. It printed 3 different values of the inner index, and then it printed that it is done with that value of I, which is 0, and then the outer loop iterated again, and for the outer index 1, the inner loop ran 3 times once again, the 0, 1, and 2, and then it once again printed, done with outer iteration 1, okay? And that's about it. I will leave it here. Jamaica, skipping over the functions. Okay. If there are any questions, yeah, please put them in the chat.
That's right. So Parjito will be here throughout the session. So if you have questions, please put them in the chat and he will answer those questions. Same thing with the first part of Notebook 1, which Lordrick is back with us as well, so they can both answer those questions. All right, wonderful. Thank you so much, Parjito. All right, Notebook 2, Bojidara, you are up.
Yes. Hello again. If anyone has joined more recently, I'm Boji. I'm gonna present the next notebook. Thank you so much to Lordrick and Aparajito for this lovely introduction to the basics. So, can everyone see my screen? Is all good?
Yes.
Okay, all is
Yep.
good. Amazing. Okay, so I'm gonna be a bit quicker, I think. I was actually worried all day that I'm gonna take less time and then not know what to do. So good for me. That might be useful in this case. So in the second notebook, we're going to look into a little bit into 2 very important packages for Python that are used for science pretty much every time you do anything. really. So what is a package? Package is some code, very basically, that someone else wrote and is giving us to use. It can involve some functions, some classes, if you want to go into the object-oriented programming, as Lodric mentioned. But it doesn't matter. The point is, it's some stuff that someone has created that we can use. So in order to use it, we need to import it. So that's where we are starting in the first cell here. We're importing two packages, NumPy and matplotlib pyplot. So what these two things do, first thing, NumPy is basically a package that helps us use, so not only use, but work with a lot of data, which is very important for astronomy and astrophysics because we usually have a lot of stuff to deal with. So we import that as import NumPy, and then we import it as np. So that means we're basically calling this package only np for the rest of our notebook. So we'll just be using those two letters because it's easier, it's quicker. It's also the standard, so you can name it whatever you want. You can name it Boji, but that's not very easy to Google because no one is doing that. Kind of the standard way to name things. There are some standard ways that people tend to name things and makes it easier to Google and work with. So I would recommend following the standard basically. So we import NumPy as NP, we import matplotlib pyplot as PLT. Again, that's the standard. This little line was for me to troubleshoot some things. I don't think that's part of the notebook. And the last line, this is, again, I think in some cases, in some configurations, not strictly necessary, but it's basically used to, as the comment here says, to display our plots in the notebook instead of opening another pop-up window. I think older versions of Jupyter used to do that by default. So let's run that. And now we should have these things imported. So we can move on to talking a little bit about what is an array. So NumPy basically is a package for working with arrays. They are kind of similar to lists in the sense that you can put a bunch of things in them. However, very different from lists because arrays require us to have the same type of object inside them. So here we're going to be working with NumPy arrays that have numbers in them, basically, floats. So we create one with this line, x equals np a range. It's very important that this is a range, not a range, because that is spelled differently. For me, that has been an absolute nightmare, since English is my second language and I keep misspelling it and reading it wrong and then not knowing what's going wrong in my notebooks. So keep that in mind. And this is a built-in function in NumPy. So again, we do np dot the function, and then we can use it because we've already imported NumPy. And then the arguments of that function are, the first one is the start, the second one is the stop, and then the last one is the step. So basically we're creating an array that is going to, I mean, you can already see it on the bottom because I didn't clean the outputs, but it creates an array that includes all of those numbers from 0 to 100 with a 0.5 step. So we have 0, 0.5, 1, and so on until, what's the last number? 99.5. Why? Because it excludes the very last number. So it's up to 100, but excludes 100. So if we want to also have the number 100 here, if we want to include that, what do I have to do? I have to make the stop be one more step away, basically. So if I do 100.5 and rerun that, we're going to see that our array now has the number 100 as well. But now in this case, okay, so we can keep going to the other line. So we're printing x. So this whole thing is our whole array. What else are we printing? We're printing the length of x using this, again, built-in function, len of x, which is showing us that now we have 201 numbers. So before, when it was only to 100, we had 200 numbers, which makes sense because when we include both bounds, we have another number. Then we get the mean of x. So here we're using a NumPy function again, NumPy mean, and this is giving us the average, which in this case, when I go all the way to 100, the mean is a 50. That makes sense. And then we have the maximum value, which we get again with a NumPy max, and then we get the minimum with NumPy min. All of those are very straightforward NumPy functions. Generally speaking, if you need to do anything with numbers that is kind of straightforward, like means, max, minimum, median, all sorts of things like that, there is probably a built-in NumPy function. Even if you don't know about it, you can Google it and it will probably come up. So you can see all sorts of data about your data, which is very useful. So you can play around with different arguments. Yes, we just did that. You can play around even more, of course. You can change the steps. So we can go in steps of 10, let's say. That's going to be a different array. Yes, much smaller, and so on. But for the sake of the notebook, let's go back to what we had before. Okay, now functions of X. We can, keep using the NumPy functions. We can create our own. So I'm going to show you how to create our own because we didn't go over that in the previous notebook. But let's first go over the built-in ones. So as I said, simple things with numbers you can do directly from NumPy. So here we have NumPy sine, x over 10, and then we have NumPy cosine, again, x over 10. So that's going to give us, what is it going to give us? Let's print it out just to see what it looks like. So when we're using NumPy functions, what they do is they do this operation on the whole array, so on every number of the array, and they output another array. So that's important. So we get the sign of every x from before over 10. But okay, let me remove that so we don't have it hanging out. I'm going to do something. I'm going to add another cell here, and I'm gonna define my own function. So how do we do that? Define, we just type def, which is just short. And I'm gonna define a function that I personally use way too much, which is going to be just drawing a straight line, basically. So that is going to be the name of our function, and then in brackets here, we're going to put the arguments that our function expects to get in order to be able to give us something back. So we're going to put x and then a and b, and I'm just gonna type. So we do a colon here, and then again, everything should be indented inside the function. And now I'm just going to write the line equation, which is y equals a times x and then plus b. I tend to put spaces a bit randomly. You don't have to be doing that. But okay, and then when I have that, I want my function to return this value to me. So I'm gonna do return y. And then this function now, if we use it, it's going to calculate basically what the y should be for every x for certain a and b. So let's check that out really quickly. I'm gonna do print line. So this is our function of x is the array that we already have defined. And I'm gonna say a is going to be 2, and then b is going to be 3, let's say, some numbers. And let's see what sort of y's we get this way. Okay, so let's do a very quick sanity check. If we take the very first x value here, it's a 0. And then we do 0 times 2, that's a 0. And then plus 3, that's a 3. And that is what we get in our resulting array. So that's what happens for all of the numbers. And that is just an example of how we can define our function. I said this is a line equation, and it is, but that doesn't look like a line. How would we make that actually be an image of a graph? Let's see. Let's go a bit down and talk a little bit about figures. So figures are obviously a very fundamental scientific thing. When we have a lot of numbers, it doesn't really make sense to be looking at them like this. It gets confusing, it gets boring, it's not very pleasant. So how we try to look at a lot of numbers is usually on a graph. Again, I have the outputs, but it's okay. We'll play around and we'll see how they change. So here comes the second package that we imported, which is pyplot, matplotlib pyplot. which is helping us um, create graphs. So let's go line by line. First thing we have is PLT, that was the package, dot plot, just a very simple one, X, Y1, and then let's first plot only that, and then I'll show you what the rest of the things are. Can I? Okay. So this is the simplest plot we can possibly make. We're just using the plot function, giving it an X and giving it a Y. And the Y, let's go back just for a second. Y1 was sine of X over 10. So we get, what do we get? We get a sine. That's kind of sine curve. That's what we would expect. This is the default behavior. We get the blue line. We don't get any axis labels, anything like that. So that is not very useful in science terms. I don't know what this graph is showing me at all. So then we want to add some additional arguments to make that more readable and nicer. So let's have a look at what they are. We're adding, for example, a label. So the label is going to tell me what I'm plotting, especially if we're plotting multiple things, as we will in a second. It's very useful to have them labeled. We're giving it a specific color that we want it to be. We're giving it line width, so making the lines a bit thicker so they're easier to see, and line style, which in this case is dashed line. That's a very small subset of all the arguments you could be giving to these functions. Matplotlib is extremely flexible and customizable. You can pretty much do anything you have ever imagined with it. And I would encourage you to have a look at the documentation and have a look at what sorts of things you can change. But pretty much anything about these plots, anything can be customized if you try hard enough. I'm playing around with this line a little bit. This is the plot legend. This is because if we have a label, if I just do it like that, we're going to see, so we see the changes to the line, but we don't see the label anywhere because it has nowhere to go because I haven't plotted the legend. So we need to also plot legend in order to be able to see that. And here it is. We have a little legend that's telling me this line is representing y equals sine of x. Okay, let's plot some other lines. We also have y2, so let's not, why not plot that as well? To put that on the same plot, we just do the same thing again underneath. Here we have x, y2, we have a new label, we have a different color, so they're easier to differentiate. And we are again increasing the line width just to see a bit better. We're not adding a line style in this case, so we're letting it have the default behavior. The default behavior is just a solid line. So that's how this looks. We have a sine and a cosine, and as you would expect, they're the same but shifted compared to each other. So that's great. That's what we wanted to see. Okay, but again, still we have no axes. I still don't know what any of this means. So let's have a look at that. We can plot X label and Y label. So those are going to give me the axis labels. And we're just giving them some larger font size to see a bit easier. That's all. Again, the labels are also very customizable. In a lot of ways, when you change their font sizes, you can change their positions. You can change a lot of things about them. Let's see how that looks. Yes, so I have X and we have a Y. Amazing. That's great. Okay, but again, we can see that our plot goes from a little bit below 0 to a little bit over 100, and then on the other axis from a little bit below -1 to a little bit over 1. That's again the default behavior of Matplotlib, is to kind of see where your data is and just give you a tiny little bit around that. But what if you want to zoom in or zoom out or see something different? Then see different parts of our data, then we can use the for example, y-lim. We can also use x-lim. This is changing the limits, in this case on the y-axis. So we're changing them from -2 to 2. So what do we expect to see? We expect to zoom out in the y direction. So let's see if that's truly what happens. Yes, now we can see we're going from -2 to 2, and our lines, there is a bit more space below and above them. Another cool thing you can do with that is if you need, for whatever reason, to invert the axis, the easiest way to do that is to just switch the order of those two numbers. So if I want to go from 2 to -2, I can do it like this, and then y is just going to flip. So Yeah, so now we see a mirror image of what we had before. And that is useful sometimes in some situations in astrophysics, quite a lot actually. Okay, so let's go back to what we had originally. That is what you should be having in your notebooks, and that's what we get. Fun. Let's move on a little bit. Let's play with some new functions of x. Yes, a lot of functions of x, and we're going to see some more plots. So, starting again with an x, this time between 0 and 1 in steps of 0.01. And then we're putting a bunch of functions here. Let's go through them quickly. So we get a y2, which is x. Double asterisk is what? It's an exponent. So x to the power of 3. Then we get y3, which is x to the power of a half. So that is a square root of x. And y4 is some function 2 times x minus x squared. Fun. So let's check out what these things actually look like in a picture. Again, I do have the output, so I'm sorry, but okay. Let's run this cell and have a look. So again, we are plotting x, we're plotting y, we're increasing the line width, and we're giving it a label. These labels here, in this case, because we want them to have the mathematical functions, we're using the LaTeX notation. So what that means is we put an R in front of the string, and that's telling Python that we want to use, that's telling matplotlib that we want to use LaTeX notation. And then we're putting all the math stuff in between the dollar signs. That is just, again, from LaTeX. And then we do y equals x. And this time we're using a different symbol for the exponent because, again, that's not the Python, that's the LaTeX notation, and to the power of 3. And then we do that for the other labels as well. So okay, in this case, we're not telling Matplotlib specifically what colors to use, and we still see 3 different lines that have 3 different colors. That is, again, the default behavior, which is the first line is always blue, and then we get orange and green, and there's a bunch of other colors as well. So you don't necessarily have to define the colors by yourself. It's just that generally I don't want to talk for most people. I personally find the default colors kind of ugly, so people usually try to change them just for aesthetics. And also, if you have a lot of lines, sometimes it gets confusing. You might want to group them in specific ways. You want to have your own color map more often than not, but not necessarily. Okay, so what else do we have going on here? We have a legend again, this time slightly smaller, font size 12. And the legend, so we see here where in the previous plot, we just had the legend with no argument. So that's the default behavior for a legend. It goes somewhere, wherever Python decides there is enough place on your plot, it puts the legend there, and that's what you get. In this case, we're asking it to change the font size to 12, and we're asking it to put it at location 0. 0, I think, is the default behavior again. I learned just today, actually, when I was playing around with this notebook, that the options for putting the numbers go from 0 to 10, which is a lot of options. So if we put some weird number, let's say 12, that's going to give me an error. Yes, you can see that's an error. And it's telling me it must be a string, coordinate tuple, or an integer from 0 to 10. So let's try those out. So, okay, so a string just means putting in quotations where you want it. So upper left, let's say, that should put it again where it was before. So it's just talking to Python in plain English. The way it goes with numbers is that 1 to 4 are the 4 corners. So it starts if we start at 1, it starts at the upper right corner, and then it goes anti-clockwise. So that's 1, that's 2, 3, 4. Let's do a weird one that I didn't know about. Let's do 10. That's in the center of your figure, which I have never seen anyone use. It's a bit wacky, but I guess in some sort of figures you might be interested in having that happen. So that's pretty
Don't
cool
tell
that
the
it's an
exoplanets,
option.
guys.
Yes, we don't have an exoplanet person here, right? To murder both of us for joking like that. Okay. Okay. So going back to the default. And then again, we have the X and Y label. In the previous plot, I forgot to mention, so it's important that we put those in quotation marks so we can see the actual string that says X instead of what will happen if I remove the quotation marks. Now that is the variable named X, which is what? It's an array. So we're going to print out the whole array, which is not very pretty and nice. So we want that to be in quotes. And the last thing I wanted to say, when you're plotting things like this, when you want to plot a function, you want it to look smooth. So you want to use enough numbers to make your function look like that. So what would happen if I change the step to something larger? Let's say I do 0.3. Now that's not a very smooth plot because in this case I only have like 4 numbers and I calculate the y value only for those 4 numbers and then they just get connected with straight lines in between them. So those are not the functions we're trying to plot. So we want to use something that's small enough that it looks smooth, but it's not too small that your computer has to do too much work because that's just unnecessary and it takes time. So that's how we get our smooth lines. Actually, if we zoom in a little bit, I think, can I zoom in? Oh my God. We can see here, I don't know, I can see a little corner here a little bit because this part of the function is a bit steep. It's a bit hard to see because it is smooth enough with this many values. But if I add another 0 here, for example, it's going to take a bit more time. But then we don't get that little corner at all. Now it's all very smooth. So that's a bit of a give and take when you want to plot functions. And I think that's it from me. I'm sorry, a bit quick, as I said. I don't have anything else to add, so I hope that's okay.
No, that's
But yeah,
perfect.
play around, Google things, and enjoy, I guess. That's the basics.
Thank you so much. And yes, yes, as each of the mentors have continued to say, play around with it, try it out yourself. Please do that because it's going to increase your confidence when using Python, and you'll get to see just how much you can learn with trying things out. And that's why I love these notebooks because they're already set up for you. You see exactly how to do it. You have people who you can connect with during the sessions or afterwards. You can email me. I can pass those along if you have any questions after the sessions. All right, we're ready for notebook 3, and that's going to be Geronimo. And since we are kind of running a bit ahead of time, let's continue. We could end a little early, and it gives me more time to edit the recording and send it to you all. So Geronimo
Nice.
is going to be doing Notebook 3, and Notebook 3 is the color magnitude diagram activity. Hera, take it away.
Nice. Okay, let me know when you can see my screen.
We can see your screen.
Perfect. Okay, so let's get started with a bit of notebook 3, and this is a very exciting point, I think, for the activity because it's after the tools that we gathered with the help of Lord Rick of Aparajito and of Uboji, we can finally use Python as a tool for working on some astrophysics. So that's very exciting. So here in this activity, we will start constructing something that is often called a CMD, or a color magnitude diagram. So you will see often this acronym being thrown around. It is something that we will elaborate on during the activity, but it was discovered, or like maybe just first constructed by some astronomers during the 20th century, and it is a very key cornerstone of modern astrophysics because it started just like as a funny pattern that we could see if we organized two measurements that we could do from observing groups of stars into a very nice plot, and noticing that there was like patterns that told us something about the physics of the stars we were observing. So it is quite an interesting tool. So we're gonna use here like just a group of stars. We have like a list of information and like different variables that were measured for this survey called Splash, and they're stars in the Andromeda Galaxy. So that is like a very important first step to know what data set we're working with. And we're gonna start just first by importing our libraries, like the libraries that we're going to be using. So as mentioned before, we're going to be using NumPy, we're going to be using Matplotlib pyplot, and yeah, we're gonna just mostly focus on those two, which help us first store our data in arrays, and then that's going to be very efficient for manipulating the data, doing operations on it, and then plotting it nicely, as Boji was showing us using Matplotlib. So that's really fun. Um, I think Philip that designed this nice notebooks, he did a very cool job of setting up first the environment of the plots that he wanted to build. So there is a couple of cells here at the beginning where he mentions these are his preferred settings, but these are not like mandatory cells. They just will make the rest of the job quicker for us and also have some aesthetic value to it. So for example, these first two is like if you're writing or like doing some document on PowerPoint or in Word, this is just setting the font and setting the font size of your plots. So this is going to be set for the rest of the plots that are that generated after this cell. So then, oh, we have a. Oh, I guess I didn't run the first one. Wait. So I love Python because it will tell you when you're messing up something and you have to go back and check if you actually ran things properly. So perfect. Okay, now we have our font size and our font defined. And then here we have a few commands that will, this is a function that has a few commands that will initialize the plots that we're going to generate. So we'll simply just create the canvas on which we're going to paint our beautiful color magnitude diagram. So feel free to just run it without paying too much attention to it. But if you want to look into each line, the first one that says F, just like this one just generates like a frame object, and this one will set the size of the figure, so you can constrain the dimensions of the figure that you want to make. This one will constrain the view that we have to a specific range of values in the x-axis, so that x-lim that Boji was mentioning. And then here, when we plot it, you'll notice something that Boji was mentioning that is very much useful in astronomy, and is that the limits in the y-axis are defined first with the bigger number 24 and then with the smaller number 18, because for some quantities in astronomy we like to flip the axis and like look at them the other way around. This is more thanks to tradition and how we measure the brightness of stars, but I'll mention a bit more about that later. And here we have just simply the two labels that we're going to talk about more in detail soon. So this is simply the function that will help us make our nice plots. And then here we have a function that also, this one, I will not go into detail on it because it will take a lot of time to explain the logic behind it. This one is mostly just to make it quicker to choose a set of stars that we will pick from a set of conditions after we do the activity, and simply save those stars into a separate document with the data extracted. So we have a catalog, that's what we call a catalog, that was taken with the telescope, and that just has like all of the stars available to us for this activity. And we're going to separate different stars according to if they belong to different groups. So we can create a new catalog that comes from saving the stars that are part of each group, taken from the bigger catalog. So that's kind of the idea. So I'm going to stop to explain all this. This is just going to be something that we will call to give it a name, set some parameters, and then it will just save a file for us into our folders. So now with everything all set after running those first few cells, we can go into extracting the data that we have in our catalog as a starting point, big catalog. So this was taken together, combining data from the Keck Observatory, which is operated by the University of California in Santa Cruz. So that's pretty cool. And we have a very cool team of scientists that routinely do observations from there. And I want to stop to do a quick ad for the Shadow the Scientist program, which is really, really cool, which is why I'm here. Actually, I learned about this beautiful team and about the Python tutorials because I started attending the Shadow the Scientist program because I was just hyped up to check out how astronomers were observing the sky, and then these guys were like, yeah, we're gonna stream, like live stream an astronomer taking observations live from Hawaii, like from the peak of Mauna Kea, where the Keck Observatory is located. So that's pretty cool. And then it also has data from the Hubble Space Telescope. So we can navigate to see that we have like this data set. If you go to the home tab that opens when you run the Jupyter Notebooks, and if you have downloaded and extracted the notebooks in your own machine, wherever you have them, for example, in my case, it's here in the documents folder, and then I have the SIP Python workshop also subfolder in it. There is this folder called data that will have the Keck HST .txt. So this is a .txt file. Very often you will see that this kind of format is used for storing data. There is many others, but this is a conventional one for many things. And if you open that file, so just double click on it and it will open in a separate tab. It will let you see what are the values that are stored in different columns. So here, separated by spaces, we have first two comment lines. So they start with this hash, and that means that they are not going to be read by a Python program as information that is useful for the code. Is more useful for the user, is for the person that is writing code or reading the data to know what they are handling. Because imagine if you just didn't have this information, like if you just had like a string of numbers, as a human, like that really doesn't tell you anything. Like you really don't know what you're looking at. So we have this first two strings to keep some context on the document. So first two columns are going to be the right ascension and declination of the star. So this is just each row represents the information for a different star. And right ascension and declination are just the two main coordinates that astronomers use to locate a point on the sky. So you can look more into that if you're interested, but it has to be defined in a specific way. And each star has their own right ascension and declination. We can think of it similarly as of if you're in a different point on Earth, you will have some unique coordinates assigned to your place. So I don't know, your house has a specific longitude and latitude that is assigned to it, or like your town, your city. So this is the same for stars. You can define a system that allows you with two angles to locate any star on the sky. Then we have other two angles, which are here called Xi and Eta. These two angles are not as universal as the right ascension and declination. They are proper of this specific catalog, and they are just two angles that will tell us how far away the star that we're working with is from the center of Andromeda, the galaxy. So apparently, as you observe on the sky, the telescope was pointing a certain angle, let's say in the X and the Y directions from the center of Andromeda. And that is how Xi and Eta are defined and saved into this. This will be useful for one of the following notebooks, not for this one, but it's good to have everything in the same catalog. And then we have two weirdly named columns that are just like a string of letters and numbers. And this is because these are just two Hubble filters. So these are simply in a specific kind of notation that the Hubble collaboration defined to know which filters they were working with when observing a specific target. And filters are simply that when you observe a star, you constrain the light of a specific color to be recorded. So if you change filters, it's like when you wear like this little 3D glasses that have like a blue filter, red filter. So that's like constraining the amount of colors that you can let pass through the lens. So that's what's happening with filters, and astronomical observatories will have many different filters. And if you get into astronomy, you'll see that that is actually huge um, a huge source of problems sometimes, because you need to standardize which filters you're working with, or each observatory has to design especially with space observatories, they end up designing their own specific filters that the community that works with the data coming from those observatories will be more familiarized with. So these are the kind of the stereotypical names for Hubble filters. They're usually F and then number and then W, I guess, because maybe this is because it's like the wide field camera 475. These are not random numbers. They're usually tied to the notion that physics uses to connect with color, which is wavelength. So in this case, this might be a wavelength of 475 nanometers, let's say, and this would be a wavelength of 814 nanometers, let's say. I am not exactly sure of this, but this is what I would say with my astronomer brain that is not used to working with these data sets. But yeah, maybe Boji, if you've worked more with Hubble data, maybe you can correct. But yeah, so then from Keck observations, the Keck Observatory, which is, as I was mentioning, in Hawaii, it's a ground-based observatory. It's not in space, it's in ground. It has a very cool instrument called a high-resolution spectrograph. And with a high-resolution spectrograph, you can, by a method that we will see tomorrow, you can measure exactly the velocity that a star is moving, if it's moving away or towards you. You can exactly, like with very high accuracy, how fast the star is moving. And we call that the radial velocity, and here is measured in kilometers per second. So this second to last column will show us what is the measured velocity that we see in each of these stars. And then the last column is just a really good practice in science, which is the error measurement on that velocity measurement. So that is simply how certain the instrument was of that measurement of the velocity of the star. It's like when you measure something, say with a ruler. So if you have like a ruler like this one, you will be sure of measuring something. Say if I measure something and it measures 2 centimeters, or like, let's say if we have a more imperial units audience, if you measure it 1 inch, your ruler will have these tiny marks that will constrain how accurate, how certain you can be of that measurement. So that's what we call the error. So in this case, in any measurement that you make in science, it will be preferred if you can report how certain you are of the measurement that you're making, and that's this last column about the error. So yeah, now that I broke down this whole document, we can go back to the notebook 3, and we will go back to importing that .txt file that has the catalog, the Keck and Hubble catalog, and save it into a set of arrays. NumPy is very smart for this because it really has functions that can do everything. And in this case, we use this one that is called loadtxt. So since we're going to feed it a txt file, we can use np.loadtxt to generate an array from data stored in a txt file. In this case, we can also take more advantage of it and make it even more convenient by not just saving it to a single array, which will have like all of the columns and everything like as a single entity, but we can save it into, how many are these? 7? Yes, no, 8. 8 different arrays, which are the columns that are in our file. So remember that this file has right ascension, declination, blah, 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 all the way till the velocity error. We can tell NumPy, please, I'll give you this file, please save it into 8 different arrays. And then each of the arrays that I'm getting out of this, it corresponds with one of these columns. So that is very convenient, because then we have a full column that is only right ascension, a full column that is only declination, and so on to the filter magnitudes that we have here, and the velocities. Now, coming back a little bit into what I was mentioning of the filters of the Hubble telescope, or the filters of any telescope. The thing that the astronomers during the 20th century that I was mentioning that started making color magnitude diagrams found out is that if you measure the brightness of stars in different filters, you can play around and find out things about the stars just by doing that, just by observing them, how bright a star is in specific colors. So in this case, they defined the quantity that in astronomy is known as color. We will talk also more about this tomorrow. But as a summary, it's simply subtracting the brightness of a star into different bands, is what we call it. So it's just different bands, which are ranges of wavelength, where we let the camera store light from the target that we are observing. So the color is defined as just the subtraction between those two quantities, between those two brightnesses, or as are often called in astronomy, magnitudes. So that's why it's called the color magnitude diagram, because it's connected to the astronomical notion of brightness, which is measured in magnitudes. Magnitudes are a very funny quantity. So first, let's just run this. This line will only generate our arrays, as I was mentioning, and it will create a new array that is called color from subtracting the brightness of all the stars in each of the two bands from the Hubble spacecraft. So we run that one, and now we can just plot our color magnitude diagram. If we recall a little bit what Boji was teaching us, we can use matplotlib. This is done here with scatter, but this is just to not do it with plot and have all the dots connected with weird lines. Scatter does exactly, works exactly the same, but it will simply not connect the dots with lines. But it's the same. You could do this with plot and simply explicitly tell the function to not connect the dots. But this is another way to do it. And then the two arrays that we're gonna plot is on the x-axis, we're gonna plot this color quantity that we define. And on the y-axis, we're gonna pick one of the two brightnesses, one of the two magnitudes, and we're just gonna plot that. So this is why it's called the color magnitude diagram, because on the x-axis you have color, on the y-axis you have magnitude. And we're gonna add some other parameters, because as Boji was telling us, we can define the color of the dots that we're plotting. Maybe we can choose the size of those dots. So that's what this s=3 function is doing. And yeah, here this edge colors is just telling us don't put like a boundary with the color around the dot markers that we're putting on the canvas. So if we run this, this first call of the initialize plot function is simply generating our canvas, and then this plt.scatter is populating it with all the dots from our arrays. So if we run that, let's see if that works. It's taking a little while because maybe it's many plots. Or maybe, I don't know if I missed some, let me check real quick. Maybe I have to add a show, maybe. That would be annoying.
The plt.show, yeah.
Okay. Yeah. Let's see. Yeah, so depending on the version of your notebooks, the plt.show line might be needed or not. Like it's I've been growing up with Python, and I've moved from needing it first, then not needing it. Now we need it again. So, okay. Whatever works, you know? So now we have this, which is a color magnitude diagram. I want to move a little bit just to mention an example of a color magnitude diagram in like science that is very, very relevant. This is from the Gaia spacecraft that has been gathering data on millions of stars for the past 10 years, I think, or more. And if you do the color
it's
from
over
two
a
different
billion
bands,
by now.
it's over a billion, exactly.
Well, I mean, this I think this is from DR3, right? Gaia
Yeah, this is the
DR3.
older one. This is
Yeah,
DR3,
I think this has over a billion stars.
DR2, actually, yeah.
Oh, DR2. Yeah, I think it is over a billion. Anyway, yeah.
Yeah. So this spacecraft is incredible because it has allowed us to measure the distance to, yeah, Spargito was mentioning billions of stars to incredible accuracy and really uh, um, very clearly find our place within our own galaxy. And that is a very cool result. And a very important central part of this was thanks to building diagrams like this one. It's often called the Hertzsprung-Russell diagram because these were two of the many astronomers that worked with this kind of data sets, but they were like the main ones to popularize it during the 20th century. But they didn't know exactly what was going on when you plot like just brightness here and then color on the x-axis. I mean, they found out later with other astronomers, but at the beginning it was just like, hey, if you draw a diagram like this, you get this interesting groupings in different regions of the diagram. So they started defining that stars, depending on different conditions, could fall within different areas of the diagram. And nowadays we know that this big thick part in the middle is called the main sequence. And it's, for example, where our sun is like where stars spend their more normal part of their life in, you know. And then you have other structures like what's known as the giant branch, which can be divided there into the asymptotic giant branch, or yeah, there's different categories that have been assigned because with the passing of time and more detailed studies on stellar astrophysics, we learned that the position in the color magnitude diagrams, it's totally connected to the evolution stage of the star. So that was a very powerful result that we use routinely nowadays in astronomy. So if we come back to the one that we're doing, it will not look exactly the same because we are looking at a very specific population of stars coming from the Andromeda Galaxy. And also, it is with a very different instrument. So all of these factors into to make it not look the same. But even in this one, we can already recognize like there's like 3 different regions, right? Like we have like 3 different clusterings of stars in this catalog. So you have some group here to the left that is clearly separated from the others. And then here, there's not that much of a clear boundary, but you kind of notice that there is like a little gap here that is kind of curved, where there's like a thick cluster here in the center. And then there's like another group above that that is kind of more sparse. So we can assign those to, from what we know about stellar astrophysics, we can recognize astronomers that some of these are red giant branch stars, others are asymptotic giant branch, and then we also have the main sequence. So to start, we can use the tools of NumPy and Matplotlib to cut slices of these and visually separate them, and then also save them in different catalogs. Those are the catalogs I was mentioning earlier that we want to save them in. So we can start by recognizing that the left part is what we will define as the main sequence. The part here on the left, which is bluer stars. They are, as I was mentioning, in the main part of their life cycle. They are more conventional stars, let's say, quote unquote, while the ones to the right that are going to be redder stars are stars that are older, that are already in the final stages of their evolution as stars. So we can start by, yep.
It's the color of a star. I mean, color in the colloquial sense, not the astronomical sense, but also color in the astronomical sense. Both of these things depend on the temperature of the star.
Yeah.
And like Hero showed you in the HR diagram, the color you can see is the label for the x-axis below, and for the x-axis above, the label is surface temperature. And that's basically, the temperature is basically what's reflected in the astronomical color, and also how you visually see the star. So cooler stars appear redder, and or rather stars with cooler surface temperatures appear redder,
Yes.
And stars with hotter surface temperatures appear whiter and bluer. And you can see that the other two axes are magnitude and luminosity. So magnitude is obviously, as Hero explained, what we see as the brightness, what we can observe. And luminosity is kind of what you calculate theoretically, because magnitude will depend on a few things, right? It will depend on how far away the star is. And so that's the apparent magnitude, but absolute magnitude is when you adjust for the distance. In our case, we assume the distance is more or less the exact same because the galaxy is so far away that the difference between different parts of the galaxy barely matter. So we don't specify absolute magnitude or relative magnitude because it's all the same. It's all the same. But luminosity is basically what you can theoretically calculate, taking into account any gas and dust that might be between us and the star, obscuring some of the light that might affect the brightness. So luminosity is what it's actually like. That's what we are calculating. And surface temperature and luminosity are the two variables on a standard, HR diagram. But we are doing observational astrophysics here. So yeah, that's what Hero is taking through the color magnitude diagram. Sorry for the interjection, Hero. Go ahead.
No, perfect. Thank you. That is a lovely comment on the astrophysics of this, because it is really, really important, really interesting. Yeah, so we are here, focusing on the observational aspect, so we can measure how bright things look from Earth with our telescopes, and then to do the jump into how much power is being actually emitted on those stars. That requires other steps, and it's a different problem. But it is very important to make it, and that's how you make these kind of diagrams that are more precise and more informative, and will connect the information we observe from telescopes to actual surface temperatures on stars. To me, that's one of the most fascinating facts in astronomy, is that we are able to determine how hot a star is without having to go and plug a thermometer on its surface, because also that would be impossible. But even if we could reach a star, because that's it's impossible to reach it. Stars are into temperature levels that are hard to directly measure, and it's crazy that we can do that just with observational tools, just from hundreds or thousands of light years away. Okay, we have a couple more minutes, right, Jamika? I think almost done.
Yes, that's right.
Cool. So to constrain that, to draw those lines on the plot, we can start by first following. So this is what you will see if you run this notebook. We can start by drawing first the main sequence of this color magnitude diagram. So let's just run the cell as it is, and then we will fill up the rest very quickly. And also I have to add probably here where I'm plotting stuff, plt.show. Very important. So you'll see that I managed to separate the part that I will call the main sequence and just color it differently than the rest of the group of stars. So this is very cool because of a property that we can use in Python, and is that we can take arrays and verify if a condition is satisfied, as we were seeing earlier with Apergito and with Boji and Ludwig. So we can check for the ones that have the color below 1.75, because that's just by eye. You can try to calibrate it and change that value and see if something works better for you, depending on where you can reach the right group of stars according to what you see visually on the diagram. And also you can limit the brightness to being higher than 23rd magnitude. Here, notice that I say like the magnitude will be lower than 23, but that means it's brighter stars. So since we have our axis flipped, we have to kind of flip our brains a little bit on that one and think, okay, I want to catch everything that is above this 23 line, and then everything here is going to be part of my main sequence, but that means it's going to be smaller because I'll be going to smaller numbers. So that's, pay attention to that, because that's why this is why the y-axis array, the magnitude in the F814W filter, has to be smaller than 23. You can also, again, tweak that one and see if a different selection seems to work better for you. And then we just initialize another plot where we're gonna plot the same thing, but then on top of that, we're gonna add the selection of each of the arrays, color, the magnitude in the filter, that where only these conditions are satisfied. So if these conditions are satisfied, this MS array is going to be an array of saying where it is true that that happens or where it is false. And then when you call that as the argument of another or like as the index of another array, is going to only give you the places or like the values of color where MS is true. So where the main sequence is true. So we simply here also add plt.text. That's another useful, more visual command that just gives us the ability to put a text tag on somewhere on the plot. Here we give it this two coordinates just by eye, just so we have this MS written here. You can also play with those coordinates, move it around, and see if there's a different place where you would like it better. And then we will use the write catalog function. We'll simply call that function to save all of the arrays, the right ascension, the declination, xi, eta, the filters, all of it. So everything that we were mentioning before, but where the main sequence condition is true. So the stars that we tag as main sequence, all of their information is going to be saved in a different catalog that is going to be called mscatalog.txt. So we're simply saving it with a specific name. You could change this name to something different, but just to keep track of it and know that this is our main sequence catalog from this data, since we know that, we're simply going to call it mscatalog.txt. And here we add also this line because this function was written in a very smart way, where you can also keep track of what each of these quantities that you're saving means. So to do the other part of to separate the other part of the data set, we will simply notice that here we have a curve that seems to be like the boundary between these other two groups. So we're going to define that curve, and just because that's how we work a lot of the times in science, we think of something that looks like a mathematical model that we know, and we try to apply that and see if it works. So a mathematical model that seems to work here, I would say, seems to be a parabola. So if we were to use like a parabola right here, we could maybe divide the two populations and use that as the condition on which we select the other two catalogs. So we can simply, I will do it very quickly. It says we can have the parabola equation, which is this one right here, and we can replace the numbers for things that would work. I had set aside some numbers that work, so I'm gonna just simply type them in, and you can play around also, because it doesn't mean that they are the correct ones. It's just that those seem to work for me, but check for yourself. So notice how this is the equation for a parabola or a quadratic equation. If we go to a graphing calculator and we type in that equation, so it's a, which is just one constant that you set, x minus h squared plus k. This h and k are offsets, so it will allow me to move right or left my parabola, and then the k1 will be up or down. And then the a is going to help me modify the amplitude of the parabola, and I can make all of them like change with time, and then you have crazy parabolas that do funny dances. So if you want to play around with a model, like if you think something that you see in nature, in this case, in one of these data analysis activities, fits with a mathematical model that you want to fit to it, you can first write down the equation of the model that you're thinking of, and getting more familiar with it is very, very helpful. So here, like, oh, if I change this parameter like this, what does it mean for the distribution that I'm showing? So here, that's why we use this equation. And what we do is, okay, let's see where the brightness, so the brightness of the y value is higher than the parabola. So what that means is, since it's going to be higher, it will be down, since our y-axis is flipped. So we're going to select everything that is under the parabola in this case. And then also we need to separate it from the main sequence. And remember that we selected the main sequence to be under, so to the left of 1.75 value in color. So I will select the rest. So it's like to the right 1.75. And we can add that to the plot. That should be easy enough if we simply copy how we plotted also the, maybe I can take away the show, because I will do that on the same plot. So we can add that to the plot simply by replacing. So this one we don't need because we already plotted all of the catalog. And this one, instead of MS, we will switch that for RGB, because those are the stars that now we are plotting. RGB, yes. And we can switch the color to differentiate it from the MS to green. And now we also want a tag that says that those are the RGB stars, but I'm going to move it, I don't know, somewhere more to the right. Let's say 6. I don't know. Let's try if we keep it there. How it looks like. So now look that our boundary is more noticeable here, when the ones that are now green that were before gray, and they got the tag RGB, which got put in blue. I'll switch it to green just to be more consistent. And then we can do exactly the same with the AGB stars, which are the ones that are left, the ones that are up here, but simply by flipping the condition that we set. So it's also going to be to the right of 1.75, but now it's going to be under, like, or above in this case, the parabola. So it's going to be a lower magnitude for that. And if everything looks right, let me check. So let's say, let's keep these ones green now that I think of it, the AGB ones, and these ones, because they're the red giant branch, let's make them red. I think that would make more sense. Red. So yeah, so we set the condition here, and now we're gonna call that AGB, not RGB, but now AGB, asymptotic giant branch. And then we're gonna switch where it says RGB for AGB, AGB, and this one I'm gonna have to put maybe higher up, let's say 19 or something. Maybe should work. That's green. I think everything looks good there. And now we're gonna just delete this show, so we show it at the very end. And we're almost done. Nice. So now you see that we have split our 3 populations within the group of stars that we're observing in our catalog. This is only separated visually in the plot. We have to save the other 2 catalogs. So notice that we called here the right catalog function for the main sequence. We can simply just copy that and just put it under the RGBs, for example. Simply make note of calling it something like RGB catalog. And then the data sets that we're saving is where the right ascension is RGB, the declination is for the RGB, and so on and so forth. You will simply replace that in all of the indexes of all the arrays. And that's simply how you would do it. Sometimes it gets a bit tedious if you have many arrays, but you can also automate that with other smart Python tricks. So this one, let's just sanity check it. We're going to save it on the RGB catalog.txt, and each of the arrays that I'm saving in that catalog are the ones where the RGB condition will be set to true. So wherever RGB condition is true, it's going to save a value for all of the variables that we have for each of the stars. So that ensures that we're only keeping track of the stars that we care for that specific population. So we can go ahead again and copy that and do the same for the AGB stars. So in this case, AGB to the plot, and then we can write the AGB catalog. So we simply switch, in this case, the R's for A's, and that's going to be easy enough. And that's also the good part of writing organized code where you're keeping track of the names of things. It becomes more comfortable, and if code gets messy, it is really a pain to catch errors. When your code is more organized, it's a bit easier to catch errors, check if everything is working properly. And no errors here, so that's good. So we have visual confirmation of what we did, and also whatever is saved here in blue is saved also in a new file called main sequence. And whatever saved here in green is on the AGB file, and the red is for the RGB file. And that is lovely. And also we can simply run these other two lines that will tell us more informatively how many stars did we actually find in each of these populations. So we can just check the length of any of these arrays from the original catalog, and that will give us the number of stars. And then we can simply sum the amount of stars in each of the condition arrays, or like the tag arrays that we call main sequence RGB AGB, and divide it by the total amount of stars, and then we get the fraction. And then we'll see that if we do the union of those sets, we'll find how many we actually selected, and because there's going to be some that just didn't make the cut for any of the filters. So those ones, it's also useful to keep track if you're having any like leftover stars that maybe are falling out of your selection criteria, and it's also relevant. So we also write here like which ones were not selected. This little squiggly line is the not operator. So we'll do the opposite of the selected, so the not selected, over the total amount of stars. And this is simply going to print how many stars we have in each of the categories. So we have fraction of the main sequence is about 15% of the total catalog. RGB is about 55% almost of the total catalog. AGB is 14%, and then we just did not select about 16% of the population. So that's it for now for notebook 3. Make sure that you can follow along and go over it a couple of times. Make sure to play around with the conditions that you put here on the quadratic model. Maybe even think if there is something better than a quadratic model to fit this little gap right here. Like what happens if you do cubic? What happens if you do other kinds of curves that you know about from your maths learning, and that might help you catch different amounts of stars into different populations or different categories. So yeah, that's it for now. Keep your catalogs handy because they're going to be useful for I think for the final notebook tomorrow.
That's right.
And yeah, and that's it for me.